a king, queen, or jack, they are independent, right? So it means, they are mutually exclusive. So it means we can just add their probabilities. We have 4 kings, 4 queens, 4 jacks. That's 12 out of 52, right? Because there's 52 cards in the deck. If you look at the top of that little picture, it says there's 52, that's a 52-card deck. How about clubs, hearts, and spades?
39.
So yeah, so there's 13 of these, 13 of those, 13 of those. So it's 39 out of 52. That reduces to 3/4. This one up here reduces to 3 out of 13. How about king, queen, or diamond? Are those mutually exclusive? No, they're not. So here we've got 4 kings, we've got 13 diamonds, we have 4 queens, but we have this king of diamonds and this queen of diamonds that are getting double counted. Right, so the king of diamonds is getting counted in the king group and the diamond group. The queen of diamonds is getting counted in the queen group and the diamond group, so it's getting counted twice. Does everyone see that part? So the probability would be I have 4 here, 13 there, 4 there, but I have to subtract these 2 guys here, the overlap. So out of 52, you'll end up with 19 out of 52. You guys need 15 seconds to discuss with your neighbors? Yes? Okay, take 15 seconds. Go ahead.
That's good for the server, so they can try to do
All right, now you guys are just chatting about other stuff. Come on. Okay, so at this weekend, there's a couple things that I want to talk to you guys about. Every once in a while, I'll have like 2 things or 1 thing or 3 things that I just want to talk about that are not math related. The first thing was, after hearing about Kobe Bryant's death, I was thinking about a couple things. I was like, I should share just a couple basic things. One is, I don't know what happened, but maybe like you're a pilot, right? You're flying a helicopter, you've got a big star, you don't want to piss him off, he wants to get somewhere. So you're like, well, I probably won't crash. What's our guideline for unusual? For unlikely or unusual in statistics? You guys remember what our guideline is? Remember?
Often never repeatable.
5% or less. If something is 5% or less likely to happen, we would consider it unusual or unlikely. That's our general guideline for statistics. So, and it's unlikely, but if you're talking about your life, well, if you're talking about just getting in an accident, you might be like, well, 5%, not so bad. 1%, not so bad. If you're talking about dying, that's a pretty major thing, right? Someone said, there's a 1% chance you will die doing this. I would never do that. That is way too big a chance to take with my life, right? So I don't know, but and certainly if it was like a commercial flight like United, like if United had helicopters, they would probably never do that. I remember when I was flying, it just reminded me of when I was flying out over the break. My family was flying to Japan. We were going from SFO to LAX and then direct flight to Narita, to Tokyo. And so a couple things. One is, and then there was fog, so we got delayed. And you're just kind of like, gosh, we're thinking, I hope it clears up, I hope they fly out. And we don't really worry about it like, I wish they'd fly anyways, because we kind of realize, everyone kind of realizes, if they don't fly in fog, it's not, you don't want them to fly in fog. You know what I'm saying? If it's not safe, you don't want them to do it. Even if it's a tiny chance, because the probability of you, even if it's only a 1%, even if it's a 1 out of 1,000% chance, 1 out of 1,000 chance, it's too big a chance to take with your life, right? So maybe people will be a little less aggro about trying to make the flight happen, even if it's foggy now. where was I going with this? So a couple things, yeah. I know, it's so sad. But there's two things that you should know. First of all, just general things. One is, if you have a connecting flight, never fly out of SFO. Because they get fogged in. Maybe not very often. 1 in 100 chance. But you're SOL if that happens to you. We miss our flight, and the guy's like, oh, well, the next flight we can get you on, because everybody else is in the same position, and there's 5 of us, is Sunday. So you'll arrive, we're supposed to arrive 2 days before our cruise takes off. You'll get there 2 hours after your cruise leaves, right? And they've managed to find some other way. But so the one thing is, if you're connecting, first of all, if there's an issue with the plane, obviously don't get upset. Well, you can get upset, but don't don't wish that you could get on that plane, because if there's something mechanical with it, you don't want to get on it anyways. We kind of realize that, right? If it's maybe unsafe, even if it's only a maybe, you don't even want to take a chance with maybe when it comes to your life. The second thing was, we talked about it, one of the stewardesses said, or the flight people, they said, ideally if you're taking a connecting flight, especially a connecting flight out of the country, that first flight, you want to get there the night before, or at least several hours before. And I usually try to cut it really fine. I'm like, hour and a half, I can make it, right? But maybe I may make it 2 or 3 hours now, just to give myself a little bit. Depends on what it is, right? If it's just going down to Cabo and that's it, no big deal, then that's fine. Then hour and a half's fine. If I'm a little late to Cabo, big deal. But if it's like going across the pond to catch something like a cruise that you're kind of screwed if you miss that, then that's something to think about. Maybe you try to give yourself a little more space out there. And like I said, the other thing is, if you get a chance to take a connecting flight, Oakland, San Jose, don't skip SFO. Don't do SFO. So that's my advice for future. My total math advice. All right, moving on. Let's get back to math. Oh, I was going to say something else, which I guess is sort of related, which I didn't say the other class, and I kind of meant to, was if you think something nice about somebody, say it, right? I mean, it doesn't cost you anything to just tell them. Like, you got a friend, you think, oh, they're so helpful about blah, 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 or they're so good at blah, blah, blah. Why not just say it, tell them at some point, right? Because people just don't say that often enough. And you never know what's going to happen, right? Okay. So back to this. Multiplication rules and probabilities. Vicki, read, please.
Multiply rules and the conditional
Probability.
Two events A and B are independent events if the fact that A
Occurring.
does not affect the probability of B
Occurring.
occurring.
Great. So in other words, independent if A happening doesn't affect the probability of B happening. So let me give you some examples here. First, let's take a look at cards. So hearts and kings. Does drawing a heart give you any information about whether it's a king? So first off, what's the probability you draw a king? How many kings are there? 4. So the probability of drawing a king, so capital P, probability of, parentheses, a king, is equal to 4 out of 52. Great, that reduces to 1 out of 13. Now, what if I tell you it's a heart? The card to drawing is a heart. I looked at it, I know it's a heart. So you know it's one of these. Now what's the probability of drawing a king, given you know it's a heart? So here are the hearts. How many are kings? 1 out of how many cards? 13. 1 out of 13 chance. Everybody follow that? You know it's a heart. So that's 1 out of 13. So are these the same probabilities? Is 1 out of 13 the same as 1 out of 13? Yes, it probably hasn't changed. So that means that it's independent. The event heart and the event draw a king are independent. Because knowing one has happened, in other words, knowing that it's a heart, for example, doesn't change the probability that it's a king. Please note a couple things. Both times we're looking at the probability of a king. So this is probability of a king, this is probability of a king. This is a probability of a king given nothing. This is a probability of a king given that it's a heart. But either time, both times, it's a probability of a king we're comparing. All right, so here is another scenario. Now I change the deck. Here's my deck here. Here's the king of hearts. I'm going to throw it away. It's gone. Now, how many kings do I have left in here? 3 out of 51. Now I have one less card, 51 cards. So my probability of drawing a king is what?
3 out of 51.
3 out of 51. Reduces to 1 out of 17. Now I tell you, oh, by the way, I looked at your card. It's a heart. Probability that's a king given it's a heart is what? 0. There are no king of hearts in the deck. So if you know it's a heart, your card's a heart, what's the probability it's a king? 0. It can't be a king because there are no king of hearts. Everybody good with this part? So here, the probability has changed from 1/17 to 0. So these are dependent. Because knowing it's a king has now changed your guess. Before, if I said, hey, I'll give you $10 if you draw a king, you had a 1 out of 17 chance to win $10. Knowing it's a heart, you have a 0 chance of winning this $10. Good? So those are dependent. Likewise, if you had stacked the deck and put in a whole bunch of kings, king of hearts, like 5 king of hearts, then it would also not be the same. It would change kind of the other way. Okay. But either way, as long as those probabilities are not the same, it's dependent. Here's another example. I'm going to take 5 cards. Oh, they're all mixed up. No. Uh-oh, I had a fixed deck. I didn't have them on. Does anybody see like a few cards lying around? Randomly? Oh, here they are. Okay. All right, so that was not a whole deck before. Oh well. I have 1 through 5 here. Ace through 5 of hearts. And mix them up. Have something to draw. What's probably she draws an ace?
4 to 52.
1 out of 5. Here, draw a card. What'd you draw? 2. All right, good enough. Good deal. I'm going to mix them up again. Now it's probability that she draws an ace. 1 out of 5. Makes sense? Same. Hasn't changed. Draw a card, don't move. Now, what's the probability that she draws an ace? 1 out of 4, or if that's an ace, 0 out of 4. But it's different. It's changed depending upon what she drew. Does that make sense? So when you draw a card and you replace it, then that's independent because the probabilities stay the same. But when you draw a card and you keep it, you don't replace it, then all of a sudden the probabilities are different. They're dependent upon what you drew the first time.
Nice cards.
Yeah, I love these cards. All right. Now we're going to talk about, so replacement is something we're going to do a lot. Replacement is when you draw something, you look at it, and then you replace it. You put it back. You don't replace it with another card or another marble. You replace it with the same exact one. So you guys following? So whenever I say with replacement, it means you draw it, you look at it, you put that same one back. Without replacement is when you draw it, you look at it, and you keep it, and you don't put it back. Good? So make sure we're clear on that. It's going to come up a lot in the next couple of weeks. Flipping a coin and rolling a die. All right, so here's my die. What's the probability I roll a 4?
1 out of 6.
1 out of 6. Great. Now, aha, I flipped the coin. My coin is heads. Now that I flipped the heads, now it's probably I roll a 4.
1 out of 6.
Still 1 out of 6. It hasn't changed. So these two things, flipping a coin and rolling a dice, are independent events. You guys with me? So this is, because this is 1 out of 6, sorry. This is still 1 out of 6. They are independent. Good? This one is what we call, this was probability of a 4. This is probability of a 4 given heads. Please note, both of them are probability of 4. Probably 4 given nothing, probably of 4 given heads. You always have to compare the probability of the same thing. I wouldn't compare the probability of rolling a 4 to the probability of heads given I rolled a 4, right? Because it's not fair to 1/6 to 1/2. That makes no sense. That should never be the same, or it's rarely going to be the same, right? I wouldn't say, oh, they're dependent because rolling a 4 is 1/6 and rolling and flipping a heads is 1/2. We know they're independent. Everybody follow that? Should be rolling a 4 and rolling a 4 given something else. Should always be the same thing that you're doing the probability of. Do you guys need 15 seconds to converse with your neighbors about this? It's kind of you got to wrap your head around it. Once you do, it's a fine, but you got to wrap your head around it. Yeah.
Could you explain the independent and dependent again for the roll and the die for independent?
Right. So if your probability doesn't change, it's independent. If your probability changes once given something else has happened, then it's dependent. So the probability of rolling a 4 is 1/6. Now something has happened. I flipped the heads. The probability of rolling a 4 given I flipped the heads is still 1/6. It hasn't changed, so it's independent.
Okay.
If this became 1/5, like draw for card, drawing an ace. Drawing an ace is 1/5. Drawing an ace, given they replaced it, is 1/5. Totally fine. Drawing an ace, given someone else has drawn a card and not replaced it, that changes. It's right. So then that's dependent.
Okay.
All right, we'll look at this a little bit more here. So here are the events, chocolate and male. So the idea is just knowing it's male, give you any information about whether or not it's a chocolate lab. So what's the probability it's a chocolate lab? Let me ask you that. Chocolate lab? 8 out of 20? Now, given it's male, here's the thing about given. Whenever you get given, just take a second and circle. What am I given? Am I given chocolate or given male? Given male. It just reads like it is. Probably chocolate, given male. Given male means it's male. Just circle it. It takes like 5 seconds. This is on your sheet. You guys should be doing this now. Circle the males. Now, what's the probability of chocolate given male? 6 out of 12. Everybody follow that. You only care about the circle part. 6 out of 12. This is 0.4. This is 0.5. Are those the same? No. So is this independent or dependent? Dependent. It hasn't changed. Depends upon whether it's male or not. Right? So probability of chocolate is different than probability of chocolate given male. So knowing it's male changes it. Why don't you guys try this one? Is it independent or dependent? Got to figure it out. Find the probability it's female. Find the probability it's female given it's a yellow lab. Find those two probabilities. Oh, female? I'm sorry.
Yeah.
Okay, it's female.
Which is what it says. Yeah, but probably it's female and male.
Given that it's a.
Oh, yeah. I thought it was given that.
All right, so what's the probability that it's female?
It's 0.4. 8 out of 20.
8 out of 20. 0.4. Great, now, given, what's probably it's female given it's yellow? Take just a second to circle the, is it given yellow or given female?
Given yellow.
Given yellow. Everyone, everybody, take a second, circle the yellows then. Do it. What's the probability that it's female given it's yellow?
6.
4 out of 6. 0.667. It makes it a lot easier if you circle it. Are these the same?
No.
No. So is it independent or dependent? Dependent. Here's another way of looking at it. It's all about proportions. So female and yellow, what are the proportions? What are the things that matter to me when I'm talking about females? So first, find your total females. Everybody on board? Try to find your total yellows. Circle those. Find your total female and yellows. Which ones are the female and yellows? Anybody? Yep, the 4. And then find your grand total. Those are the ratios you want. You want 4 over 6 compared to 8 over 20. Those are the ones you just found earlier, right? So this is comparing ratios. It makes it a lot easier. If you just kind of look at those are the ratios you want, those 2 things. Those 4 things, you can draw the line either way. You can actually draw the other way too if you wanted to. You could compare it. You could also compare it, these 4, this way. If you wanted to, you could do 4 out of 8 to 6 over 20. You can compare it that way as well. And either one of them works. So your question could be, the first one would be, is 4 over 6 equal to 8 over 20? No, right? So it's dependent. If you go this other way, you could say, is 4 over 8 equal to 6 over 20? And that's also no. So it's dependent. The side-to-side ratios and the up and down ratios will either both be the same or both not be the same. I'll show you guys in a minute what I'm talking about here. So let's take a look at this other one. So here we're looking at chocolate and male. What are the 4 numbers that I want to circle here? So, Sarah, give me one. 6, 4, and 2?
Yeah.
Those ones? Nope. Try again. Talk to your neighbors. Chocolate and male. Which things are important to chocolate? Okay. Okay. So chocolate. The total chocolates. Yeah, that's important. What else is important with chocolate and male? Total males. Anybody on board with that? And then we also want the ones that are chocolate and male. Yep. And then it needs to make a perfect rectangle. So the other one should be 20. Everybody on board? The total is always in there. So we can look at the ratio of, is 6 over 8 equal to 12 over 20? That's a question you could ask, right? 6 over 8, the same as 12 over 20. Someone see those proportions? 12 over 20, 6 over 8, yes? And the answer was no, so it's dependent. You can use any of those methods we just talked about to do the, flip the page, do the next one. Yeah. So if you're not sure they're equal, find them as decimals. Right, just write them out as decimals, and that'll tell you whether they're equal.
I think it's supposed to be notation. Yeah. So I guess it doesn't.
Oh, you're saying of those two.
Did you get the second one fresh? We had chocolate. Oh, and then just the female chocolate. Okay.
All right, let's take a look. What's the probability that you pick a puppy and it's female? 15 out of 40. 0.375. Now, female given chocolate. Given what?
Chocolate.
Chocolate. So you're going to circle all the chocolates, the whole section. What's the probability it's female?
3 out of 8.
3 out of 8. Which is 0.375. Make sense? So is this, are chocolate and female independent or dependent? Independent. Here's the other thing. I could go with the ratios. What are the ones I care about? The total female, the total chocolate, the grand total, and what's the other one that completes my rectangle? The 3. So 3 over 8 compared to 15 over 40s. And see if they're the same. Good? They are the same.
So as long as they're equal in the
Yep.
ratios, that's independent.
I'm sorry, then they're independent.
That's all that's.
Yep.
Okay.
Yeah, I could have done 3 over 15 to 8 over 40, and those are also equal. Those are both 20%.
Copy that.
So that's how you test for independence. That leads us to the multiplication rules and conditional probability. Let's have somebody read this one and see how they do. Brendan, M.
multiplication rules and conditional probability. Multiplication rules, probability of A and B equals the probability of A multiplied by the probability of B. Independent.
Perfect. Well done. So if they're independent, like remember like my flipping my coin and rolling my dice, you just multiply their probabilities. The next one. Let's try someone else on this one. Rizzo. Go ahead. This one here.
The probability of A and B equals the probability of A times the probability of B given A.
Nice. Great. So if it's dependent, then you find the probability of A. So kind of think of it like your tree, right? It's branching. Probability of A. Now I'm here. Then you need to find the multiply by the probability of B given A has happened. I've already taken the step to A on my tree. I've gone that pathway, so I know A has happened. So probability of B given A has happened. Make sense? So that's where this comes from. Keep reading. Go ahead and read the last part.
The conditional probability of B given A means the probability of B given A. Given A has happened under the condition that A has happened.
Good. All right, so you guys do lab 3, tossing a coin. So first, flip a coin. What could happen? Draw a tree for your outcomes. And then, if one thing happens, then you roll a dice and see what those outcomes are. If the other thing happens, you roll a dice. See what the other outcomes are. So no matter what you're doing, you're flipping a coin. No matter what the outcome is, you're going to roll a dice from any one of those positions. Does that make sense?
So they're different trees?
No, one tree. Put them together.
So you flip a coin.
Flip a coin. So, flip a coin. Something can happen. And then from here, you're going to figure out what happens if you go there. You're going to have some branches off of there when you roll a dice. Or you could go here. And again, you're going to have some things that happen when you roll a dice. So, you flip a coin, what could happen? Heads or tails. And then you're going to have stuff happening from here, and you have stuff happening from there.
Okay.
Is that, you guys following me? Okay.